In this work, we introduce PlaneDepth, a self-supervised monocular depth estimation method via orthogonal planes. For the outdoor drive scenes, we propose to use photo-parallel planes and ground planes to model vertical objects and the ground, respectively. This approach enables us to segment the ground in a supervised manner and predict smooth depths for the ground, which is important for the autonomous driving. The predefined planes provide depth candidates for each ray. Based on this, we propose to model the depth as a mixture Laplace distribution along the ray, with each candidate representing the mean of a perk in the distribution. We also address the issue of artifacts caused by occlusion in the post-processing with our bilateral mask to further improve the self-distillation labels and final results. Since the widely used resizing curving augmentation causes the ground slopes, the ground and the vertical objects become no longer orthogonal. We have to rectify our ground planes accordingly. Which could be seen here, we rectify the parameters of predefined planes using the resizing curving matrix, ensuring that they remain parallel to the ground. However, we found that the network still hardly uses the ground planes. This can be attributed to the variations in ground depth candidates for each pixel caused by the rectification process, so the network has to predict the current rectification first and then predict the depth, which makes it hard to learn. To address this problem, we impose the parameters of resizing curving during training via neural positional encoding to inform the network about the current rectification status. In this way, we can attain improved segmentation and smoother depths for the ground. Previous methods warp source image to the reference wheel using planes, and then compose them to a static image before computing the L1 error, which introduces a non-trivial challenge. Different weights may result in identical static color. To address this challenge, our mixture Laplace loss actually computes the error individually on each warped plane before composition, while incorporating the inherent uncertainty of the distribution. This approach enhances training stability. We minimize the negative log likelihood of the probability distribution as our loss function. As done in the previous method, if we always use left wheel as input and compute the loss on the right wheel, the occlusion will only occur on the left side of objects in the left wheel. So all depth artifacts caused by occlusion will appear on the left of objects in all input image. Take advantage of this. For each single input image, we can get two depth maps, one with only left artifacts and another with only right artifacts. Then together with the occlusion mask computed from probability volume, we can filter the artifacts. Similarly, if we apply the widely used post-processing to further improve the results, the artifacts will occur on both sides of objects. Then, we could filter them with our bilateral mask to get better post-processing results and self-distillation labels. Extensive experiments demonstrate the effectiveness and efficiency of our method. Thank you for watching. Here are some video results if you are interested.